Have you ever taken an empty soda can and just crushed it in your hand? Or maybe you've bent a paperclip back and forth until it finally snapped. It feels totally mundane, right? But what you're actually doing is performing an everyday scientific miracle. Welcome to This Explainer, where we're going to unlock the microscopic secrets of metal. You see, when scientists first crunched the numbers on perfect atomic crystals, they realized something kind of baffling. Based on the incredibly strong interatomic bonds, metals should be rigid, brittle, and literally impossible to bend without shattering. And yet, they bend. So today, we're diving into the invisible atomic-level flaws that make our modern metal-formed world possible.
Okay, let's think about a standard aluminum beverage can. It starts its life as a completely flat sheet of solid metal. And then, through a series of deep drawing operations, the walls of the can are stretched and pulled into that familiar cylinder shape. Just pause and really think about that for a second. We are taking solid, room-temperature metal and stretching it like it's warm plastic. It doesn't shatter into 1,000 pieces like glass or ceramic would. No, it seamlessly yields and takes on a completely new, permanent shape. If we zoom way in, say 150 times magnification, we can see exactly what's happening beneath the surface. In its original state, the aluminum has a grain structure where the grains are equiaxed. That basically just means they have roughly the same dimensions in all directions, kind of like a microscopic tiled floor. But after the can is formed, it's a totally different story. The grains themselves literally stretch out and elongate in the direction of the applied force. So that massive shape change of the can that we see with our own eyes is a direct result of this intense microscopic stretching.
Now, scientists actually have a specific name for this physical stretching. They call it plastic deformation. And unlike elastic deformation, where you stretch a rubber band and it just snaps right back, plastic deformation is permanent. But here's the catch. To achieve this permanent change, there has to be a net movement of a massive number of atoms. And to move those atoms, billions upon billions of interatomic bonds have to be forcefully ruptured and then immediately reformed in a totally new position.
Which brings us right back to that discrepancy we talked about earlier. If you actually had to break all of those atomic bonds at the exact same time, it would take an immense, almost impossible amount of force. I mean, the theoretical strength of a perfect crystal is off the charts. So how does it happen? Well, enter the unexpected hero of our story, the dislocation. A dislocation is basically a linear crystalline defect. It's an internal flaw. And paradoxically, it's exactly these flaws, these imperfections in the atomic lattice that actually give metals their malleability. Without dislocations, perfect crystals just wouldn't bend.
So there are two main ways these microscopic defects show up. First, we've got the edge dislocation. Picture an extra half plane of atoms wedged right into the crystal lattice, causing a localized distortion. When stress is applied to the metal, this extra half plane moves parallel to the direction of that shear stress. Then, on the flip side, we have the screw dislocation. This one is more of a shear distortion that creates a continuous spiral ramp of atoms. And interestingly enough, a screw dislocation actually moves perpendicular to the stress direction. But here's the key takeaway. Even though they move in totally different directions relative to the applied force, both of these defects achieve the exact same result: permanent plastic deformation.
Now, when these dislocations move and deform the metal, scientists call that process slip. And it's crucial to understand that this doesn't just happen all at once, it happens step by discrete step. First, it gets triggered by an applied shear stress, just like the force used to draw that aluminum can we talked about. Next, the interatomic bonds sever right along a very specific plane. Then, that extra half plane of atoms shifts over by just one single interatomic distance. And finally, the dislocation line traverses all the way across the crystal along what we call the slip plane.
Let's break down exactly how this slip process begins. Imagine an initial extra half plane of atoms, we'll call it plane A, wedged right into the top half of the atomic lattice. Now, when that shear stress is applied from one side, it begins to push plane A across. And as it moves, it starts pushing directly against the top halves of the neighboring atomic planes. In a very next fraction of a second, the tension builds. If that shear stress is strong enough, the bonds connecting the top and bottom of the adjacent plane, let's call that one plane B, are suddenly severed. Boom! Plane A links up with the bottom half of plane B. So now the top half of plane B becomes the new extra half plane. The dislocation has shifted exactly one atomic distance over. And the wildest part? Behind it, it leaves it perfectly ordered, beautifully reformed lattice. It literally only disrupts the structure right at the exact spot where the extra half plane is passing through.
Okay, if visualizing billions of invisible, shifting atomic planes is kind of making your head spin right now, don't worry.
Scientists actually use a brilliant biological analogy that makes this instantly intuitive. The motion of a dislocation through a crystal lattice is almost exactly like the way a caterpillar moves across a leaf. Think about how a caterpillar actually inches forward. First, it pulls in its very back pair of legs, which creates a little hump near its posterior end. Then, rather than trying to lift its entire heavy body all at once, it just ripples that hump forward. It repeatedly lifts and shifts just one pair of legs at a time. Finally, when that little hump reaches the very front, the entire caterpillar has successfully moved forward by 1 unit of distance. So the absolutely crucial point here is this direct mapping. The caterpillar's moving hump, that is exactly the same concept as our sliding extra half-plane of atoms. By moving a hump just one pair of legs at a time, the caterpillar avoids the massive energy expenditure of jumping. And by moving the dislocation one atomic spacing at a time, the metal avoids having to break all of its atomic bonds at once. It breaks a few, shifts, reconnects. Breaks a few, shifts, reconnects. That right there is the fundamental secret to how solid metal flows. Now you might be wondering, where do all these defects actually come from in the first place? Well, they're a completely natural, unavoidable feature of the material. All metals and alloys contain some dislocations right from the moment they're born. They form during the initial solidification of the molten metal, they get introduced by thermal stresses during rapid cooling, and of course, they multiply massively during any sort of previous plastic deformation. Because these defects totally dictate how a metal is going to behave, scientists obviously need a reliable way to count them, so they use a metric called dislocation density. This is basically defined as the total length of all the dislocation lines in a specific volume, or even more commonly, it's just the number of dislocations that intersect a random square millimeter of area. And let me tell you, the numbers we're dealing with here are absolutely staggering. In a heavily deformed piece of metal, like, say, a piece of steel that's been hammered, rolled, or bent really drastically, the dislocation density can reach up to 10 billion per square millimeter. Let that sink in. 10 billion microscopic atomic wrinkles, all packed into an area about the size of a pinhead. It's wild.
Comparing these numbers across different materials really puts the whole thing into perspective. For instance, silicon single crystals, those pristine materials we use to make our computer microchips, have incredibly low densities. We're talking maybe 0.1 to 1 defect per square millimeter. Ceramics sit a bit higher, somewhere between 100 and 10,000. But metals? Even a carefully solidified pristine metal starts out at 1,000, and heavily deformed metals, as we just saw, skyrocket into the billions. This massive density of mobile defects is exactly why metals are so forgiving and bendable, while your ceramic coffee mug or a silicon wafer will just catastrophically shatter under stress.
But all of this bending and shifting definitely leaves a permanent mark on the material. When you plastically deform a metal, it requires a lot of energy. About 95% of that mechanical energy you put in is simply dissipated as heat. Which, by the way, is exactly why a paperclip gets hot if you bend it back and forth really fast. But roughly 5% of that energy is actually retained internally. It gets permanently trapped inside the metal as stored energy, specifically existing as lattice strain radiating out from those billions of dislocations.
See, let's visualize what that trapped energy actually looks like. Because that extra half-plane of atoms is so forcefully wedged into the structure, it pushes the surrounding atoms right out of their comfortable, perfectly spaced positions. The atoms immediately above and adjacent to the dislocation line get squeezed really tightly together, which creates severe compressive strain. Conversely, the atoms directly below the extra half-plane are stretched apart, creating immense tensile strain. So what you're left with is basically a localized, microscopic war zone of tension and compression. Which leaves us with a totally fascinating and highly practical question to ponder. Every single time we shape a car door, forge a steel beam, or draw an aluminum can, we are packing up to 10 billion defects into every square millimeter, trapping 5% of our massive deformation energy as permanent internal tension. With all that microscopic strain silently screaming inside the atomic lattice, how much more stress can a metal realistically take before the entire system fails and the material finally snaps? Thank you for joining me on this explainer. I really hope this changes the way you look at every piece of metal around you. Keep wondering, keep learning, and I'll catch you next time.